Now that you've gone ahead and shown that you've done putting all your information into the Microsoft form, let's go ahead and see where any of our misconceptions were. Taking a look at this, remember we did do a modified lesson check, so it wasn't everything, just to make sure that the work was manageable. Number 34, we want to explain if the total external force acting on a system is 0, what can you say about its total momentum? Well, this was one of the first things we sort of talked about in the lecture for 7.3, in the fact that if F external is 0, then our momentum is conserved. Our initial momentum is equal to our final momentum. Number 35 is sort of looking at the same idea. We're looking at that difference between the internal and the external forces. We know that if the external forces is the same, but we're looking, again, this is sort of the went over at the very beginning of the lecture, and we're looking at the fact that internal forces may change what an individual object is doing, but they do not change what the system is doing. All right, internal does not change the momentum of the system. All right. That goes ahead and brings us to number 36. Two ice skaters at rest in the center of an ice rink push off of each other in opposite directions. We want to identify the system in which momentum is conserved and list the internal and external forces acting on the system. The one thing important to notice here is that they're on an ice rink. Right? Ice rink actually is a big indicator that we're talking about no friction. Right? So the system is going to be the set of objects we're interested in. We want the momentum to be conserved, the total momentum to remain entirely constant. So for number 36, the system is the two skaters. All right. Internal forces. Force of 1 on force of skater 1 on skater 2, and force of skater 2 on skater 1. The last sort of piece that we're looking at here in this particular case is the external force, and there's none. All right, because it is frictionless, we are looking at the fact that there is no external force in the system of our two skaters. All right, and the reason, technically speaking, gravity is going to be external to the system, but we've already looked at the fact that gravity, forces perpendicular to the direction of motion don't do work. So we are going to look at the fact that in this particular case, the gravity is not going to do anything because it is perpendicular to that motion. It doesn't matter that it's external. All right, so the internal here, no external forces. The system is our two skaters. Now we're ready for some problem solving. All right, number 39. Two canoes are touching and at rest on a lake. All right, so I have a canoe here and a canoe here. We have canoe 1 and canoe 2. The occupants push away from each other in opposite directions. Canoe 1 has a speed of 0.58 meters per second, and canoe 2 has a speed of 0.4 meters per second. If the mass of canoe 1 is equal to 320 kilograms, what is the mass of canoe 2? Well, we're looking at the conservation of momentum here. That states that the momentum before is equal to the momentum after. The momentum before is the fact that they're stationary, so our PI is equal to 0. Our PF in this particular case is going to be the momentum of the individual canoes. So that's going to be P1F plus P2F. So we're going to go ahead and set these, set everything equal to each other. So we have 0 is equal to P1F plus P2F. So P1F is equal to negative P2F. And we can go ahead and expand these out even further because we know momentum is equal to mass times velocity. So M1V1 is equal to negative M2V2. Right? We have M1, V1, and V2. We're looking for M2. We can go ahead and move everything over to the other side. And we do that, we get M2 is equal to M1V1 over V2, right? So you may notice there's a negative sign here, and masses can't be negative. That means we have something that we're missing from up here. We do know that our canoes are going to move in opposite directions. So this canoe is going to move this way, and this canoe is going to move this way when they push apart. All right? If we go ahead and keep traditional directions as positive, then this velocity will be positive, this velocity here will be negative. So that's going to go ahead and take care of all of our signs when we make arrangements over here. So I'm going to change colors so you can see what I'm working on a little bit easier. So M2 is equal to negative 320 kilograms times that negative velocity of 0.58 meters per second, all divided by that 0.42 meters per second. These negatives are going to cancel so that we do have that positive mass that we're looking for. So 320 times 0.58 divided by 0.42 gives us a mass of 441.904, blah, 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 blah. Right. We do only get 2 sig figs in this particular case, so M2 is going to be 440 kilograms. So that goes ahead and takes care of number 39 for us. We can keep going with number 40. Draw a line here. Number 40 says a 94 kilogram lumberjack stands on a 1,200 kilogram log in a pool of water. Initially, the lumberjack and log are at rest. So that goes ahead and tells us that PI is equal to 0. The lumberjack then starts jogging towards the shore along the length of the log. If the lumberjack's speed relative to the shore is 2.2 meters per second, what is the log's speed relative to the shore? So what's happening here is we have a log and we have our lumberjack. He's going to run this way, and due to conservation of momentum, the log is going to move this way. So that's sort of what we're looking at here. If we go ahead and build the same equation we saw before, I'm going to look at the fact that my final momentum is going to equal the momentum of the lumberjack plus the momentum of the log. So the momentum of the lumberjack, and we set this equal to our initial momentum. Momentum of the lumberjack is equal to negative momentum of the log. All right, just like we saw in the previous problem with the canoes. So we have the mass of the lumberjack times the velocity of the lumberjack is equal to negative mass of the log times the velocity of the log. Again, we're looking for the velocity of the log, so we're going to go ahead and solve everything for that. When we do that, I get velocity of the log is equal to negative mass lumberjack times the velocity lumberjack divided by mass of log. Right. We were given the mass of the lumberjack was 94 kilograms. We have the mass of the log is the 1,200 kilograms, and we have the velocity of the lumberjack. All right. So we do get the fact that the velocity log is negative 0.17 meters per second. Do note the fact that we already noticed the fact the log was going to move in the opposite direction of the lumberjack. Since lumberjack had a positive velocity here, the velocity of the log is going to be negative. All right, now we're ready for number 41. Let me just clean up my space so that you can see my work. All right, so let me do this in red. 41. A young hockey player stands on the ice hockey holding the 1.3 kilogram helmet. So we have mass of the helmet is 1.3 kilograms. The player tosses the helmet directly in front of him, so velocity of helmet is equal to 6.5 meters per second. And he recoils with a speed of 0.25 meters per second. Recoil means he's going to move backwards in the opposite direction. So the velocity of the hockey player is equal to 0.25 meters per second. We want to know the mass of the hockey player. All right. So one thing you should have noticed I forgot while I worked on this is these two speeds need to be in opposite directions because one of them is a recoil. So this should be negative. All right. If we want to visualize this, my hockey player is standing here. He's holding a helmet. He throws the helmet that way, and then he moves that way. So our initial momentum is equal to our final momentum. He's initially at rest, so my initial momentum is 0. My final momentum is the momentum of the helmet plus the momentum of the hockey player. So the momentum of the hockey player is equal to negative the momentum of the helmet. Right? It doesn't matter which one you make negative as long as one of them is negative on one side of the equation because that's just a matter of algebra in this particular case. So we're going to go ahead and expand these out. Mass of the hockey player times velocity of the hockey player is equal to negative mass of helmet times velocity helmet. Now we get to go ahead and do our algebra to get this mass of the hockey player by itself. So the mass of the hockey player is equal to negative mass helmet times velocity helmet divided by velocity hockey player. We have everything that we are interested in. We can go ahead and plug and chug. All right. Notice the fact that I have a negative here and a negative here. All right. That's going to go ahead and cancel all my negatives so that I do have a positive mass since mass cannot be negative. All right. And we do get the fact that the mass of our hockey player is 33. Do go ahead and round that to sig figs. It's going to be, my handwriting got crazy. Mass of our hockey player is going to be 34 kilograms. All right. And now that you've gotten your stuff corrected, go ahead and get everything turned in via eLocker.